Hi, my name is Muhammad Tariq, and in this lecture, we will discuss the threaded binary tree concept. Now, in tree traversal, when we traverse in a tree, we have two techniques to traverse. In one technique, we have the recursion uh, method. We use the recursive method and we traverse in a tree. And the second method is the stack method. In the stack method, what we do is we use the stack to keep track of the nodes. But a threaded binary tree is a different method using which we can traverse in a tree without using stack and without using the recursive technique. How can we do this? We will discuss this in this lecture. In this lecture, I will focus on the in order traversal, and I will use the threaded binary tree concept to traverse the tree using the in order traversal. In order traversal of a binary tree is either be done using recursion or with the use of a stack. We know this. The idea of threaded binary trees is to make in order traversal faster and to do it without stack and without recursion. So the main concept is traversing the tree without the stack and without using the recursive technique. A binary tree is made threaded by making all child pointers that would normally be null point to the in order successor of the node. Now, how can we do this? How it would point to the successor? I will explain this. We have two versions of threaded binary tree. We have a single threaded and we have a double threaded. Now, what is single threaded? Where a null right pointers is made to point to the in order successor. So, how it would point to the successor, I will show you. And in double threaded, where both left and right null pointers are made to point to in order predecessor and in order successor respectively. I'll show you how we can implement this. So we have a demo tree here. It's a binary search tree. It's not necessary that you would use a binary search tree. You can also use binary tree, any binary tree. So the focus of this technique is to traverse the tree without recursion and without using stack. So as you can see here, in this tree, we have some pointers which are null. For example, this pointer, this reference is null. Okay, so this currently is pointing to null. In the same way, we have this node number 20, which is not pointing to any other node, so it's a leaf node. So the same way, this 45 is also a leaf node. 65 is also a leaf node, and this leaf node is not pointing to any other node. And same here with 60, it's the left node is null. So we can use these nodes, and then we can point these nodes to the parent nodes, and then we can traverse the tree without recursion and without a stack. So what's happening here is if I want to traverse from parent to child, for example, from 50 to 40, I can use this reference, right? I can use this reference and I can move from parent to child. But what about if I want to move back, if I want to move from 40 to 50, or if I want to move from 30 to 40? So I need a reference. I need a reference to keep track of this pointer, right? So what we normally do is we use a stack, right? What we do, we use a stack, and first we store 50 here, and then in order traversal, then we store 40, okay, and then we store 30. So we store the values here, and this is how we traverse. But in threaded binary tree, we can point the null references to the in order successor. Now, who is the successor? Successor is the one which comes after. So if I traverse this tree, so the resultant of the tree would be in order traversal I am doing. It will be 30, okay, and then it will be 40, and then 45, then we will have 50, then we will have 60, and then we will have 65. So this is what I will get when I will traverse using in order traversal of this tree. So now what I can do is I can use this null pointer to point to its successor. Now, who is successor? Who is coming after? I am at 30. What's the next value after 30? It's 40. So what I can do is I can point this value to point to 40, right? I can reference this value to point to 40. Now, for 20, what I can do? What is coming after 20? After 20 is we have 30. I can reference this right reference to point to 30. Okay. So I'm implementing the single threaded tree. So in single threaded, we use the right pointer to point to its successor. So now 45. Here we have both the left reference and the right reference. Both are null. So the 45, I can use this right reference to point to 50. Now what's the next? Okay, we do not have any other references. So for 50, 50's next is 65. So 65 is then pointing to, sorry, 60. 60 is then pointing to 65. Now this is the single threaded binary tree. Now in double threaded, what happens is the reference points to the predecessor. So what does it mean? Now I have this 45. So in predecessor, let me change the color here. Let me change the color here. So in predecessor, this 45, what is coming before 45? Now before 45 we have 40. So I can use its left reference to point to 40, right? Now for 30, the right is already pointing here, and for 20, so if I am standing at 20, so 20 is the very first pointer, very first node. So it's not going to point to any other node because it's the first pointer. Okay, so for 60, what's coming before 60? It's 50, right? It's 50. So this 60 can point to 50. And for 65, so 65 is the last value, so it's not going to point its successor, but it can point to its predecessor. So the predecessor here is 60, 60. So 60's left reference can point to 65. So now this tree is threaded binary tree. And to traverse this tree, what I can do is I can simply traverse this without using stack and without using recursion, because I know how to get to its parent. Because as you can see here, I can get to parent of 20 using this reference, right? And then I can go back to the 40 using this reference. So let's see how we can do this. Let's see how we can do this. Let's remove these values and remove these values also. And let's check and let's try to traverse this tree now. So I'll start from 50. I'll come back to the 20, and first I will traverse 20. Then what I will do is I'll check if does it has a right pointer, right? If does it contain the right pointer? If it contains the right pointer, then I will check is this the threaded pointer or the normal pointer? Because we can have a threaded pointer or we can have a child pointer. Because it's not a child pointer, it's a threaded pointer. So then I will use this threaded pointer and I'll go to 30 and then I'll print 30, right? And then I'll check if it has a right or left pointer, anyone is threaded. If it's a threaded pointer, then I can move to the 40, right? I can move to the 40. And after doing this, we can also remove these pointers, right? After traversing, we can remove these pointers to make this tree as a original binary original tree, not the threaded one. So this right pointer, this right reference, it's not a threaded reference, it's a normal pointer. So I will go to the 45, then I will print 45 here. Okay, and then I will check does it have a left pointer. Yes, it has a left pointer. I can go to the 50, right? I can then go to 50. Then what I will do is I will traverse here on the right hand side. Now, what's the advantage of this? Let's just look at some of the advantages of threaded binary tree. The traversal operation is more faster than that of its unthreaded version because with threaded binary tree, non-recursive implementation is possible, which can run faster and does not require the stack management. So this is what we did. It's a bit faster and it does not require the stack management. The second advantage is more understated. With a threaded binary tree, we can efficiently determine the predecessor and successor nodes starting from any node. In case of unthreaded binary tree, however, this task is more time consuming and difficult. In this case, stack is required to provide upward pointing information in the tree, whereas in a threaded binary tree, without having to include the overhead of using the stack mechanism, the same can be carried out with the threads. So this point, the second point is again focusing that we can point to the parent pointer without maintaining a thread, sorry, without maintaining a stack, and we can then traverse from upward to downward and from downward to upward. The next point is any node can be accessible from any other node. Threads are usually more to upward, whereas links are downward. So threads, as we saw, the threads are going upward, and the nodes and the links which uh, are towards downwards. The linking is towards the downward side. So this is the distinction. Thus, in a threaded tree, one can move in their direction, and nodes are in fact circle circularly linked. This is not possible in unthreaded counterpart because there we can move only in downward direction starting from the root. So in unthreaded version, we can only move from the top direction to the downward direction. Okay, now what are the disadvantages? Do we have any disadvantages? Yes, we do have some disadvantages. Insertion and deletion from a threaded binary tree is very time consuming compared to non-threaded binary tree. So if we have a threaded binary tree and we have the links intact, right? We have the threads intact. So when you will delete, so it will be a time consuming because we need to take care of the threads also. The tree requires additional bit to identify the threaded link. The tree also requires the information about the threaded link. In upcoming lectures, we will explore more about threaded binary tree and we will see how they work. Thank you.